Well, let's go. Let's talk about Moore's law a little bit. It's
Uh-huh.
at the broad view of Moore's law, where it's just exponential improvement of computing capability. Like OpenAI, for example, recently published this kind of papers looking at the exponential improvement in the training efficiency of neural networks
Hmm.
for like ImageNet and all that kind of stuff. We just got better on this. This is purely software side, just
Hmm.
figuring out better tricks and algorithms for training neural networks, and that seems to be improving significantly faster than the Moore's law prediction.
Hmm.
So that's in the software space. Like, what do you think if Moore's law continues, or if the general version of Moore's law continues? Do you think that comes mostly from the hardware, from the software, some mix of the two, some interesting, totally, so not the reduction of the size of the transistor kind of thing, but more in the totally interesting kinds of innovations in the
Hmm.
hardware space, all that kind of stuff?
Well, there's like a half a dozen things going on in that graph. So one is there's initial innovations that had a lot of headroom to be exploited. So, the efficiency of the networks is improved dramatically. And then the decomposability of those and the use they started running on one computer, then multiple computers, then multiple GPUs, and then arrays of GPUs, and they're up to thousands. And at some point, so it's sort of like they were going from like a single computer application to 1,000 computer application. So that's not really a Moore's law thing. That's an independent vector. How many computers can I put on this problem? Because
Yeah,
the computers themselves are getting better on like a Moore's law rate, but their ability to go from 1 to 10 to 100 to 1,000,
yeah.
was something. And then multiplied by, the amount of compute it took to resolve like AlexNet to ResNet to transformers. It's been quite, steady improvements.
But those are like S curves, aren't they?
Yeah.
That's the exactly kind of S
Yeah.
curves that are underlying Moore's law from the very
Yeah.
beginning.
So,
So what's the most productive, rich source of S curves in the future? Do you think is it hardware, is it software, or is it?
so hardware is going to move along relatively slowly, like, double performance every 2 years. There's still,
I like how you call that slowly.
that's the slow version, the snail's pace of Moore's law. Maybe we should trademark that one.
That's
Whereas the scaling by number of computers, can go much faster. I'm sure at some point Google had their initial search engine was running on a laptop.
yeah.
And at some point they really worked on scaling that, and then they factored the indexer from this piece and this piece and this piece, and they spread the data on more and more things, and they did a dozen innovations. But as they scaled up the number of computers on that, it kept finding new bottlenecks in their software and their schedulers, and made them rethink. Like, it seems insane to do a scheduler across 1,000 computers to schedule parts of it and then send the results to one computer. But if you want to schedule 1 million searches, well, that makes perfect sense.
Uh,
So there's the scaling by just quantity is probably the richest thing. But then as you scale quantity, like a network that was great on 100 computers may be completely the wrong one. You may pick a network that's 10 times slower on 10,000 computers, like per computer.
mhm.
But if you go from 100 to 10,000, that's 100 times. So that's one of the things that happened when we did internet scaling, is the efficiency went down, not up. The future of computing is inefficiency, not efficiency.
But scales,
But
inefficient
scale.
scale.
It's scaling faster than inefficiency bites you. And as long as there's, dollar value there, like scaling costs lots of money.
Yeah.
But Google showed, Facebook showed, everybody showed that the scale was where the money was at.